Okay, so let's continue. So last time I finished with the abelian Chern-Simons as an example of a gauge theory. Today I'll continue abelian Chern-Simons and then move on to non-abelian Chern-Simons and then give another example of a gauge theory where you introduce matter. Okay, so let me continue with the abelian Chern-Simons. Okay, so this is a theory which was defined on M some 3 manifold. The group was the circle group. The space of fields is just one forms. And then the action was given by k over 4 pi squared integral of a wedge dA, where a is this one form. And here k is some real number. Okay, and also last time I derived the Euler-Lagrange equations. So let me remind you that the variational one form was minus k over 4 pi squared a wedge delta a. Let me just check the sign. Yep. And then given a gauge transformation, so a gauge transformation in general is going to be a map from the manifold to the group. In this case, the group is just S1, and infinitesimally, this is just a map from M to R, so a function. So you have psi, which is just a smooth function on M. So under a gauge transformation, the Lagrangian density changes by some exact form. And the expression for this exact form was k over 4 pi squared psi times f, where f is the curvature. Okay, and finally, let me also remind you the Euler-Lagrange equations. They were just the flatness condition, so the curvature is 0. Okay, so now let's check that this is indeed a gauge theory. So we have to check that the current associated to gauge transformations is exact, and we have to check that the action is preserved on gauge transformations. So I think I already checked that the action is preserved and the gauge transformations. So let's check that the current is exact. So what's the current? Okay, so this is going to be a contraction into gamma plus alpha. Okay. So if you contract psi into gamma, you move iota psi past A, which is a one form, so you pick up a sign. So this is going to be plus 4 k over 4 pi squared a wedge d psi. Okay, and then from alpha, let me just, to fix the signs, let me just rewrite this as delta a wedge a. So this is a two form, so it doesn't matter in which order you put it. Okay, so then here you're going to have minus g psi wedge A And then from alpha, you get k over 4 pi squared psi f. So again, you can integrate it by parts. So you can write this as minus k over 4 pi squared g psi a. And then from the second term, you'll get plus 4 over 4 pi squared psi f twice. Okay, so you see that up to an exact term, it's just some multiple of f, and f is 0 on the Euler-Lagrange equations, on the solutions of the Euler-Lagrange equations. So this is exact. On the space of solutions. Okay, so this is indeed the gauge theory. All right. So now let me talk more about the space of classical solutions. Okay, so I'm now going to compute the symplectic structure in the space of classical solutions and explicitly describe how it looks like. So let's assume, as usual, that our manifold is a product of some surface across the interval. So we know that in this case, we can define a canonical presymplectic structure in the space of solutions. Okay, let me also remind you that I computed the space of classical solutions last time. Actually, the space of physical classical solutions. So this space was the space of classical solutions modulo gauge transformations. That's what the physical stands for. And this was the first cohomology of M with the real coefficients, mod the first cohomology of M with integral coefficients. Okay, so now in this case, you know that the cohomology is homotopy invariant. So the cohomology of M is equivalent to cohomology of sigma, because M retracts onto sigma. So cohomology is homotopy invariant. So cohomology of M with any coefficients is equivalent to cohomology of sigma with the same coefficients. So you see that the space of classical solutions, in this case, it's just the first cohomology of sigma with the real coefficients mod first cohomology of sigma with integral coefficients. And let's say sigma is a surface of genus G, then the first real cohomology will be some vector space of dimension 2G. And this is going to define a lattice in this vector space. So this is going to be Z to the 2G. So this is a 2D dimensional torus. So here G is the genus of the surface. Okay, so now let's compute the presymplectic structure. So the presymplectic structure was minus the integral over the boundary, which is sigma of delta gamma. So if you plug in the formula that I've just erased, you're going to get k over 4 pi squared integral of delta A, which delta A over sigma. And now you actually see that this form, so you might be familiar with this kind of pairing. This is exactly what appears in Poincare duality. You take two forms of complementary degrees, you wedge them and integrate over your manifold. And Poincare duality theorem tells you that this form is not degenerate. So you get this lemma. So this omega is a symplectic structure. Okay, so let me just, again, repeat the proof. Okay, so first of all, let's understand the tangent space. So this is a manifold. Let's understand the tangent space to this manifold. So first, the tangent space is what? So how do I compute the tangent space to such a torus? Yes, so you have a vector space model lattice. Using the translations, you can identify the tangent space with this vector space. Okay, so this is the first cohomology of sigma with the real coefficients. And on this tangent space, the presymplectic structure defines some 2 form. So it defines a pairing which up to some constant this pairing is just take 2 real cohomology classes and send them to the integral of alpha wedge beta. So this is a pairing from H1 tensor H1 into R. So this is known as the intersection pairing. And Poincare duality theorem tells you that this intersection pairing is not degenerate. Of course, here I'm assuming that k is not 0. Okay. All right, so indeed, in this case, the presymplectic structure is very explicit, and it's even a symplectic structure. Okay. Right, so now let me say a little more general things. So far, we talked about the trivial principal bundle. So we had this S1 principal bundle, and I assumed that it was globally trivial. So since it's a trivial principal S1 bundle, the connection form is just a globally defined 1 form. Now let's just ask more generally what happens if the principal bundle is not trivial. So how can you define the action for Chern-Simons theory in this case? Okay, so here's a way to define it, and it's very similar to this discussion of Weissmina terms we had a few weeks ago. So suppose that this principal bundle extends to another principal bundle, which I call p hat, over some 4 manifold. So this is some 4 manifold. With the property that the boundary of this 4 manifold is just M, and the restriction of the principal bundle p hat to the boundary is isomorphic to P. Okay, so suppose this bundle extends. So this cannot be arranged always, but let's assume that's the case. Okay, then I'm going to define the action associated to a connection one form on P hat. So I call this A hat to be k over 4 pi squared of the curvature of A hat wedged to the curvature of A hat. So the integral is over B. So here A hat is some extension of A, which is a connection on P, to a connection on P hat. Okay, so let's just see what happens if I choose 2 different extensions. Okay, so suppose that I'll choose 2 bonding 4 manifolds, B1 and B2. And then you have 2 extensions, P1, P2, and you also have 2 connections. A1 is a connection on P1, A2 is a connection on P2, and the assumption is that on the boundary, so P1 restricted to the boundary of B1, which is assumed to be M, is isomorphic to my fixed principal bundle P, and similarly for P2. Okay, and the same thing happens for connections. You have connection A1, connection A2, and on the boundary they coincide. So the picture would be something like this. So let me define B, which is take B1 and B2 and glue them along the boundary, because they have the same boundary.
Orientation of one?
Sorry?
If you do that?
The orientation of which one?
Any one of the 2.
Yeah, so to put orientation on B, you probably need to take the orientation on B1 and take the opposite orientation on B2. Is that what you're asking? Yeah. Yeah, but I'm not the moment discussing about orientations. Yes, so you can also make it into an oriented 4 manifold, indeed. Okay, so anyway, so you have this 4 manifold, and it looks, so this is my B, has one half which is B1, another half which is B2. Over here you have P1, over here we have P2. This is my boundary, which is M. And on the boundary, these 2 principal bundles coincide. So again, you can also glue the principal bundles. into some p hat over b, which coincide with p1 and p2 on the two halves. Okay, and moreover, you have a connection on this principal bundle, which again restricts to A1 and A2 on the two halves. Okay, so now let's look at what happens to the action. So how does the action change? Well, so you have some integral over b1. So we have k over 4 pi squared integral over b1 of curvature of a1 wedge curvature of a1 minus k over 4 pi squared integral over b2 f of a2 wedge f of a2. Now, if indeed, as Rick said, you pick orientation of b2 to be opposite in here, then you can rewrite this as integral just over b of f of the corresponding connection, wedge curvature of the corresponding connection. This is a connection on P. But now by construction, B is a closed Four manifold. And I claim that this integral over 4 pi squared is actually an integral form. Sorry, the integral will be an integer. The integrand will be an integral form. Okay, so how do you show that? So recall from last time that this expression f over 2 pi, this was up to a factor the first term class, always defines an integral cohomology class. So if you wedge these two things together, this is also going to be an integral cohomology class. And now you take an integral cohomology class and you integrate over B. So you see that this difference is going to be k times some integral number, integer number. Okay. So now let me assume that k is actually an integer itself. Then what you see is that even though this Chern-Simons action functional is not well defined as a function, it's well defined as a function into R mod z. So it's a function from connections on this principal S1 bundle over M, which is non-trivial, to R mod z. And this is actually good enough for our applications. Okay, so for instance, you can still talk about Euler-Lagrange equations. Let me just say that the Euler-Lagrange equations in this case are still the flatness equations. And you can also identify the space of solutions. And here I'm assuming that the principal bundle is arbitrary. So this is space of classical solutions. On an arbitrary principal bundle, you can identify it with first cohomology of M with coefficients in R mod Z. So this is very similar to what we had before. On the trivial bundle, we had first cohomology with real coefficients mod the first cohomology with integral coefficients. So let me just mention the relation between these two. Okay, so for any manifold, you have this long exact sequence in cohomology. Which goes like this. So it's going to be H1 of M with integral coefficients. You can embed it into H1 of M with real coefficients. You can project it to H1 of M with coefficients in R mod Z. And then the next term is H2 of M with integral coefficients. So you have this long exact sequence. And I mentioned last time that this second cohomology of M with integral coefficients, so this is a set, and this is a set of isomorphism classes. Of principal S1 bundles. Now the space of classical solutions for any topology of the principal bundle is this. It has a map to the type of bundle into the second cohomology. And now if you want to look at only the trivial bundle, you want to consider the kernel of this map. And since this is a long exact sequence, the kernel of this map is exactly this cohomology group mod the cohomology group with integral coefficients. Okay. All right, so this is basically all I want to say about the abelian case. Now let me move on to the non-abelian case, unless there are any questions.
So I have a really stupid question. What is K useful for?
Okay. So far we so first of all, if you only consider the trivial principal bundle, it's just a real number and it comes in as a coefficient in the symplectic structure, so it doesn't seem to affect anything. In the quantum theory, it actually affects a lot, and this K, as you've seen, if you want to look at non-trivial principal bundles, it has to be an integral, an integer number, and this actually affects the quantum theory. It doesn't affect the classical theory up to a factor, but on the quantum level, it's important. All right. So non-abelian Chern-Simons. Okay, so you've already seen the action for the non-abelian Chern-Simons in your homework for today. let me remind you how it looks like. So let me fix the group to be SUN. You can look at other groups, but that's the simplest example. Let me state a fact about principal SUN bundles over 3 manifolds. Every principal SUN bundle over 3 manifold is trivial. So as we've seen for S1 bundles, this is not the case. They're non-trivial S1 bundles, and they're just classified by the second cohomology. But for SUN bundles, they're all trivial. And so this discussion about extending the action to the bounding 4 manifold, you can ignore all of that for SUN Chern-Simons and just define it by an explicit formula. Okay, so the action, okay, so first of all, the space of fields is going to be the space of 1 forms valued in the Lie algebra. So again, here the Lie algebra is what I denote by little as SUN. I hope the difference is clear. So as the Lie algebra of SUN is given by secure Hermitian matrices, which are tracelets. Okay, so this is the space of fields, which is the space of connections in the trivial bundle. And given such a connection, you can write down the action. And this is going to be k over 8 pi squared a wedge dA minus 2/3 a cubed. Okay, yep.
Oh, I was wondering about, is it really minus, not plus?
Well, so for us, it's going to be minus.
Because most of the literature calls it plus.
Yeah, it's related to the sign. It depends how you identify a connection 1 form associated to a connection. If you look at the formula for the curvature, for instance, that Anton gave you, it was dA minus a squared. Again, in most of the literature, you'll probably see dA plus a squared. So if you flip the sign of a, this is quadratic, this is cubic, so this will not change, but the sign here will become plus.
And this a cubed is a half a wedge.
Oh yeah, I'm going to mention that. So let me write the same expression in 2 different ways. Okay, so first of all, I'm going to write in terms of the curvature. So the curvature is dA minus a squared. So dA is f plus a squared. So this is going to be a wedge the curvature plus 1/3 of a cubed. So it's one convenient way of rewriting this formula. And another one is, as Rick said, so how can you interpret this for an arbitrary Lie algebra? So what does that mean? It means you take 3 elements of the Lie algebra, you multiply them together, and of course I forgot the trace. There's no real trace everywhere. Okay, so now you have 3 matrices, you can multiply them together and take the trace. But of course, this expression doesn't make sense in an arbitrary Lie algebra. You cannot multiply elements of the Lie algebra. But you can rewrite this expression so that it makes sense in an arbitrary Lie algebra in the following way. I'll just put it here. So this is going to be a wedge dA minus 1/3 of a wedge, something I'll write as a wedge a with a bracket. So what did I write here? Okay, so A is one form on M valued in the Lie algebra. You can wedge two one forms together. You get a 2 form valued in 2 copies of the Lie algebra. And on the Lie algebra factor, you can just apply the bracket, and you get a single copy of the Lie algebra. So this is going to be a 2 form on M valued in the Lie algebra G in a single factor. And now here you have another 1 form on M valued in the Lie algebra. So if you wedge them together, you get a 3 form valued in 2 copies of the Lie algebra, and then you apply the pairing given by the trace. And same thing here. So that's a more invariant way of writing it. But for the matrix group, it doesn't matter. Okay, so now let's analyze this action as before. So I'm going to write the variational 1 form, the Euler-Lagrange equations, and everything else. Okay, so I'm not going to write all the derivation because it's extremely similar to the case of abelian Chern-Simons. But let's just take a look at this action. So when you vary this action, there's a single term which involves derivatives, which is this one, A wedge dA. And this term is exactly like in the case of abelian Chern-Simons. So the variational 1 form will only come from this factor, and it's going to be identical to the variational 1 form for abelian Chern-Simons. So gamma is just minus k over 8 pi squared trace of A wedge delta A. Okay, and now the Euler-Lagrange equations, I have to look them up. Okay, so let me write the Euler-Lagrange equations, and I'll drop this factor of k over 8 pi squared by just multiplying everything by that factor. Okay, so then you're going to get 2 trace delta A wedge dA minus 2 trace delta A wedge A squared. Okay, and so recall that you have the curvature, which is dA minus A squared, which is exactly the factor here. It's dA minus A squared. So you can rewrite this as 2 trace of delta A wedge F. And so if delta A is arbitrary, the Euler-Lagrange equations are just F is 0. Again, exactly like in the abelian case. Okay. Right, so now I'll talk about gauge invariance of this action. And for this, let me remind you what happened in the homework for today. So let's say you have some G, which is a map. So let me state this as a lemma. So if you have a G, which is a map from M to the group, you can act by this gauge transformation on the connection A, and the action will change in some way. So under a gauge transformation, let me write this. So if you apply if you apply gauge transformation given by this G, the action, or more precisely the Lagrangian density, changes by the following formula. So this is going to be minus k over 8 pi squared d trace g inverse dg times a, and then plus k over 24 pi squared of trace dg g inverse cubed. Okay. So now let's see what happens to the action given this formula. So suppose that the manifold M has no boundary. Then the action, so the action is the integral of this Lagrangian density. This term is exact, so it will die, and the only term is this integral over this form. So it's going to be the original action plus k over 24 pi squared of trace, the integral over the manifold of trace dg g inverse cubed. Okay, so in fact, this defines for you some 3 form. So here you can look at this trace of dg g inverse cubed, which defines for you a closed 3 form on the group. So it's obviously closed because this is d of something. Or if you like, you can use the Morrow-Cartan equation for this. And now let me state a fact about this 3 form. So if you look at 1 over 24 pi squared of trace dg g inverse cubed, and you look at its cohomology class, then it's actually the integral cohomology class. So this is why this constant was chosen like that. To be even more precise, this integral cohomology for SUN, it's one-dimensional, so this is just the integers, and the generator of the integers is given by this formula. Okay, so what does it mean? It means that if you take this formula, if you take this 3 form on G, you pull it back to M via G, and you integrate over M, you get an integer. So therefore, the action changes again by k times the integer under gauge transformations. So if you assume that k is again an integer, then the action descends to a function on the space of physical fields. So this is the space of fields mod gauge. Into R mod Z. And again, this is good enough for us. You can still talk about the Euler-Lagrange equations, and you can still talk about the quantum theory for such action functionals. Okay, so let me take a break here, and then after the break, I'll talk about the space of classical solutions and how it looks like in this example. All right, let's continue. Okay, so before the break, I finished with gauge invariance of the action, and I explained that under a gauge transformation, the action changes by an integer constant, where if you assume that k is also an integer, So let's analyze this as a gauge theory now. Okay, so let's consider infinitesimal gauge transformations. So infinitesimally, they're given by a map from M to the Lie algebra, which I call Xi. So from this formula, you can actually read off the infinitesimal gauge transformations. So let's derive this, how they act on the Lagrangian. Okay, first of all, you have this G inverse dg. Sorry, this is minus k over 8 pi squared d trace. And to get from this formula to the infinitesimal formula, I'll just pretend that g is e to the xi, and I'll expand to the first ordering xi. So this is going to give you d xi times a, wedge a. There's a wedge here. Okay, and then, so what happens to the last term if you plug in g e to the xi and expand to the first term? So far, I just written the first term. So what happens with the last term? What's the leading coefficient of such an expression in xi?
The extent of the group.
Yeah, so it looks like the leading coefficient is trace of d xi cubed. And here I'm only looking at linear terms in xi. So that term dies. So the Lie derivative of xi acting on L is just that. Okay, and you see that this is something exact. So I'll just write this as d alpha of xi, where alpha of xi is this expression. Okay, and now let's derive the current. Let me also remind you of the gamma. Gamma was minus k over 8 pi squared trace a wedge delta a. Okay, so let's compute the current. So the current is going to be the contraction of xi into gamma plus alpha. So what happens when you contract xi into gamma? And maybe again, I'll rewrite this as delta a wedge a. Okay, so when you contract xi into delta a, I'm going to write it here. So this is the action of infinitesimal gauge transformations, and it's given by xi commutator with a plus d xi. Okay, then here you'll get minus k over 8 pi squared trace of xi a plus d xi wedge a. So this is from the gamma term. And then from alpha, you'll have minus k over 8 pi squared trace d xi times wedge alpha wedge a.
Excuse me, what is that contraction of psi with delta?
Yeah. So let me also write this as the Lie derivative of xi acting on a. So the gauge transformations acting on a. Let me just put aside. So the gauge transformation acting on a, so just the group of gauge transformations, it acts by this formula. And to find the infinitesimal action, you just plug in again g e to the xi, expand to the first term, to the linear ordering psi. So you see that A becomes A itself plus this commutator from here, and plus d psi from here, and then some higher terms. And the linear derivative is exactly the linear term xi. All right. OK, so we get something like that. Let's see. OK, so you can rewrite this as minus k over 4 pi squared trace d psi wedge A. So here we have d psi wedge A and another d psi wedge A with the same sign. So this is twice. And then the other term will be psi times A squared. So here I'm using the cyclicity of the trace to rewrite this bracket to put it on A, and then I write bracket of A with itself as twice A squared. Okay, so you get this term. And now let's integrate it by parts. Let's integrate by parts the first term. We get minus k over 4 pi squared g trace psi A. And then we'll have plus k over 4 pi squared trace of psi dA from here. And finally, minus k over 4 pi squared trace psi times A squared. Now you see here you have dA minus A squared. So this is d of something. This is the first term, plus k over 4 pi squared trace of psi times f. And again, on the space of classical solutions, f is 0, so the last term is 0, and you get something exact. Okay. Okay, now I'm going to discuss the space of physical classical solutions. So the space of classical solutions mod gauge. Okay. So this can be written as space of connections A whose curvature is 0 mod gauge transformations and I'm going to denote this by M G flat of M. So this is known as the moduli space of flat G bundles on M. Okay, let me give some facts about this space. Okay, so first of all, I'm going to assume that M is a product of sigma and the interval, where sigma is again a closed Riemann surface. Okay, so the first fact is that, okay, given a flat G bundle on M, so a flat G bundle is again a G bundle equipped with a connection whose curvature is 0. You have a natural restriction map to flat G bundles just on sigma. So you can restrict the bundle, and you can restrict the connection, and then you see the curvature is still 0. So the first claim is that this is an isomorphism. So this is very similar to how in the abelian Chern-Simons theory, this modular space of flat G bundles was some cohomology group, or some quotient of cohomology groups. And cohomology is homotopy invariant, so M is M differential retracts to sigma, so it satisfies that. And for flat G bundles, the same holds, so it's still homotopy invariant. Okay, so instead of studying flat G bundles on M, you can study flat G bundles on sigma. And the second fact is that suppose that the genus of sigma is at least 2, then the space of flat G bundles on sigma is generically a manifold. Okay, so what do I mean here? So you look at some vector space, the space of connections is just the space of one forms. Then you impose some condition, which is the curvature is 0. Now the curvature is 0, it's not a linear condition, so it's not a vector subspace, but instead it cuts out some interesting non-linear subspace. And then you moreover mod out by gauge transformations, so it's even worse. But still, generically, this is going to be a manifold. Maybe say smooth manifold. Okay, so you have this interesting smooth manifold, which is the modular space of G bundles on sigma. And on this space, by our construction, you have a presymplectic structure. So the presymplectic structure
So generically means that for most of the surfaces, I mean, what generically means? So that in some point there is.
It's not generically in surfaces. So it has some singularities. So the space has singularities, but away from those, there's an open dense subspace which is smooth. You can, I don't know, imagine something like this, some branches intersecting, then you have some point which is singular, but then generically it's still smooth. Okay. So now we have a presymplectic structure on this space. And this is given by minus integral of delta gamma. And this is going to be k over 8 pi squared integral of delta A wedge delta A over sigma. And since I just shown that the current is exact on a space of classical solutions, this form is basic, and it descends to the space of physical classical solutions. So this defines for you some presymplectic structure on this space of flat G bundles. And here's a very important theorem due to IT and Bott. This presymplectic structure is actually symplectic. So a few caveats. Here I consider where this is actually smooth. So the genus is at least 2. Okay, so I was discussing some field theory, some non-abelian Chern-Simons theory, and it gave you this extremely interesting, generically a smooth manifold. So in very interesting space, and just by our constructions, you obtain this interesting symplectic structure in this space. Okay. All right, so this is all I want to say about non-abelian Chern-Simons. And I'll move on to another example of a gauge theory, which is a gauge theory with introduction of some matter. Okay. So I'll not discuss the physical content of why I call this matter, but it's the following construction. Okay, so far we were discussing some gauge invariant quantities on the space of connections, and we talked about curvature. So we had the curvature. So it wasn't quite gauge invariant, but under gauge transformation, it transformed by conjugation. So if you have trace of f or some power of f, this will be gauge invariant. And so out of curvature, you can build some interesting action functionals like Yang-Mills or like Chern-Simons theory. And now I'm going to give some new ways of constructing some gauge invariant quantities, which is this following. So again, let me fix G, some matrix group. So you can think about UN or SUN. So some matrix group. And let's say V is a representation of G. So G acts on this vector space. So you can think about V being n-dimensional space over the complex numbers where SUN or UN naturally acts. And now I'm going to consider some map from the manifold into V, which under gauge transformations will not be preserved, but will change in the following way. So if you have some G, which is again a map from M to the group, then I'll just let phi G to be phi acting on, so let me just write it more precisely. So phi G at some point X, this is going to be G acting on phi at that point. So G was some matrix, and phi is some vector, so you can act by this matrix on this vector. So this is how phi transforms. And now let's look at this expression. D minus the connection acting on phi. So here, D acts on phi in the usual way, and then connection. So again, it's a matrix. It's a matrix values one form. So given this matrix, you can act by this matrix on the vector. You get another vector. So you get a one form valid in vectors here and one form valid in vectors here. So this is one form of M valid in V. Let's look at how this expression changes under gauge transformations. So we already know how connection changes under gauge transformations, and we know how phi changes by gauge transformations. So under gauge transformations where the connection changes like this, it's in the usual way, and phi g is g times phi. This expression transforms in a very nice way. You just multiply the whole expression by g on the outside. Okay, so let's check that. Okay, so we just need to plug in the transformation for A and the transformation for phi and compute what we get. Okay, so this is going to be D minus DG G inverse minus GA G inverse. And then from phi G, you have G times phi. Okay, so now let's look at the first term acting on G phi. So D acting on G phi will give you two terms by the Leibniz rule. So one term will be dg times phi, and another term will be g times d phi. Then the next term will be dg G inverse acting on G phi. So this is going to be minus dg, G inverse and G cancel. It's going to be minus dg times phi. Then from the last term, you get minus GA phi. Again, G inverse cancels. And so, yeah, you see that dg phi cancels with this dg phi. So you get G times d phi minus A phi, which is the expression that we wanted to get. Okay, so this combination transforms in a very nice way. So you can build very interesting action functionals. So let me give some example. Okay, so let me first say some more general example. So consider the following space of fields. First of all, the space of fields will involve connections. So one forms on M valid in the Lie algebra. And second, it will involve some maps from M into V. So this is where the connections live. And this is where the scalar fields live, phi. Okay. Now, for the action, I'll take the following expression. So, right. So let's take 1/2 trace of f wedge star f. This is like in the Yang-Mills theory. And then there will be a term that depends on phi. And it will look like this. It's going to be d minus A phi, which star d minus a phi, and I'll just apply the trace. And I have the trace here. Okay, so let me explain where no, I will not apply the trace. Let me just call it by triangular brackets, and then I'll explain what this expression, this notation means. Okay, so let's look at this expression. So again, d minus a phi, this is some one form on m values in the vector space V. So if you wedge this with star of the same, this is going to be an n form on m, because you wedged it with the star of something. And then it's going to be valued in V tensor V. And so this pairing, given by triangular brackets, is just a pairing on V. This is a pairing on V, so it's a bilinear form on V, which is G invariant, which is the following property. So if you take two vectors V and W in V, and you take some element of the group G, you can pair them, or you can first act by G, by the same G on both vectors, get another two vectors, and you can pair them. So this is what it means for a pairing to be G invariant. Okay. So this expression makes sense. It defines some action functional. And using this G invariance of the pairing, it's easy to see that the action is invariant on the gauge transformations. So again, the gauge transformations are, as I said before, the connection changes in the way the connections change. And then phi changes just by left multiplication. So why is this true? So we already know that the Yang-Mills term, the Yang-Mills action is gauge invariant because F changes by conjugation. This changes by conjugation, this changes by conjugation. Then you use that trace is invariant to a conjugation. And then here, under a gauge transformation, I've already shown that this d minus a times phi expression just gets multiplied by an extra factor of g, multiplies here by the same g, and then you use G invariance of the pairing. So this is still invariant. Okay, so this is an interesting gauge theory. And let me give a more specific example. So let me also say that you can add another term. The term of the following form. You have some potential acting on phi times the volume form on M if the potential is gauge invariant. So you've already seen this kind of term for a sigma model. So in a sigma model, you didn't have any A. Your action was just d phi wedge star d phi. And then you know that you can add this extra term, which is the potential. to the action. Now, if you have this A in the action, if you want this total action to be still gauge invariant, you want this potential to be G invariant. Okay, so let me give a specific example of such a theory. Okay, so in this case, the group is U1. And so the action looks as follows. So it's F wedge star F. There is no trace because it's just one-dimensional Lie algebra. In here, you'll have D minus, I'll put the imaginary unit, D minus IA, phi wedge star D plus IA, phi bar, so this is F of A, where A is a one form, so it's a real valued one form, and phi is a complex valued function M. Okay. So again, in this case, you have group G and the two-dimensional representation over the real numbers, or this one-dimensional representation over the complex numbers. Okay, so you have this term, and then finally, I'll add some potential term. And as a potential term, I'll take the following expression, absolute value of phi squared minus A squared squared, and multiplied by the volume form. So here A is some real number. Okay, so I think you've seen this potential when Anton discussed symmetry breaking. And this is going to be another example of symmetry breaking. But when you include the connection, it's even more interesting. Okay, so let me recall what the symmetry breaking was about. So if you look at this action functional, let's say on Rn, then you have translation invariance of the action functional. So you have the corresponding Noether conserved charge, which is the energy. And Anton computed the energy just for the scalar field. So there are states of, so there are solutions of minimal energy, which are called vacuum solutions. And for this theory, they look as follows. So the connection is just 0. And the scalar field is A times some phase. So theta here is some real number. Okay. Actually, so for this to be true, I think you need a minus sign here. Okay, so then when you write down the energy will have a plus sign here. So you want to minimize this term, and this term is minimized when absolute value of phi is A squared.
So what's the energy?
I prefer not to write it down completely in this case.
So in general?
So if you drop the connection, the energy
No, maybe the question was that we decompose M to something like the product of the time axis and...
What is the...
Yeah, in this case.
the differential energy, yes. So here I'm assuming that M is a product of time space, and you have a translation action along the time direction, and this action function is invariant under these translations, so you have the corresponding Noether charge, so you have the energy. Yeah. So I think maybe Anton discussed the case when you look at the Minkowski metric, and then you have the time, and then you just write down the Noether charge for that. Okay. All right, so you have these classical solutions. And now let's look how the action looks like near a classical solution. So near a classical solution means that you assume that A is going to be A naught plus some small correction, A epsilon. Phi is phi naught plus, again, phi epsilon, where I'm assuming that these are small. And where this A naught phi naught is a vacuum solution. Okay, so let's just take this expression for A and phi and plug it into the action. So I'm going to expand it near that solution. Okay, so then the action is going to look like this. So first of all, you have f wedge star f, and f is just dA. So this is going to be dA epsilon times wedge star dA epsilon. So this is easy. And then from the second term, you're going to get d minus A epsilon phi naught. So here, so it's a vacuum solution, so I'm assuming that A naught is 0. And phi naught is A times e to the I theta. Okay, so this is my phi naught. Let me just substitute it here as well. A e to the I theta plus phi epsilon. And then wedge star d plus, sorry, there's an I A epsilon A to the minus I theta, so this is phi bar plus phi bar epsilon. And I'm only going to look at terms which contain A epsilon, and I'm only going to look at quadratic terms in A epsilon. Which is the leading term. So plus some terms containing the epsilon coming from the potential. Okay, so this is going to be dA epsilon wedge star dA epsilon. Forget 1/2 here. So now let's look at what happens to the quadratic term in A epsilon in this expression. So it's going to have A epsilon acting on this A times e to the I theta. And then there's another A epsilon acting on A e to the minus I theta. So the e to the minus I theta, they cancel each other. So what you get is A epsilon wedge star A epsilon. Then here you have A squared. And that's it. And then plus higher terms. In A epsilon and plus other terms which involve phi epsilon. So for the moment, I'm only interested in the connection. Now what you see is that near this solution, so if you just look at this action in terms of A epsilon, the gauge invariance has disappeared. So this term is not gauge invariant, A epsilon wedge star A epsilon. So if you add d theta, then this is not going to be preserved. And this is an example of a gauge symmetry breaking. So even though you have a gauge, theory, near a vacuum solution, the gauge symmetry is lost. And let me just remark that this is important in physics. This is known as the Higgs mechanism. In quantum field theory, so this is the mechanism where you start with a gauge theory. So gauge theories are particularly nice. They're renormalizable and so on. And then you add some terms which still preserve the gauge symmetry, but such that near a vacuum solution, the gauge symmetry is lost. So if you're sitting near a vacuum solution, then you don't even know that there's a gauge symmetry. It looks like there's no gauge symmetry, and this is, for instance, the reason. So in physics, there are these particles called W and Z bosons, and they have mass. So in the gauge theory, the particles cannot have a mass, but because of the symmetry breaking, they acquire mass. Okay, so I'm going to stop here, and this is the last lecture on classical field theory. And from next week, we'll start quantum field theory and talk about perturbation expansions and so on. Okay.